Shifts and masks. Let's start by looking at this binary number. And we have the base 10 representation up top. We're going to try to solve the problem of trying to figure out if an integer is negative. And this is just a 1 byte integer, 8 bits. And what we're trying to find out is if we give this function is negative, some integer, it should give us back true or false. Tell us whether true it's negative, false it's not negative. For the integer 0, we can look at it and say that yes, it is in fact, it is not negative, so that should return false. How do we know that? Well, the last bit is the negative bit for integers. So if we look at that last bit, we can tell if a number is negative or not. In this case, 0. So the number is not, the 0 is not negative. Then we have a different integer, 64. Again, we look at the negative bit, it is 0, so this is not a negative number. We can look at other numbers, say like negative 24, and we'll notice that the negative bit is on, so this should return true, it is negative. And then we look at a number like negative 58, and we'll look at the negative bit, and we'll try to return that, yes, it is negative. But how would we do that? The easiest thing to be able to do this is through shifting. So again, if we have a number like 58, we look at the last bit, it's not negative. So with shifting, we can try to figure out how to return true or false. But what does true mean and what does false mean? For a computer, all that false means is the bit representation 0 or hex 0. And for true is anything that is not 0. It can be 1, it could be a million. As long as it's not 0, it's true. So we can agree that these two representations help us figure out Boolean values true and false. But how will that eventually help us? Well, we can look at the bit representation of true and notice that the first bit is going to be on, and then for false, no bits are going to be on. So if you can figure out how to get all bits in an integer to be off, then we'll be able to return false. Let's look at our negative 58 number again. If we look at the last digit for the negative 28 place value, we can try to figure out how to move that digit to a spot where it will help us with true or false. So let's try shifting. So shifting, what it does is that it's going to literally shift all the bits to the right. This is a shift right of 6 places. So if I shift right 6 places, I'm going to bring in 6 zeros from the left, and I will shift all the other numbers that were in there to the right. And these other numbers that got left over just sort of go away, and we end up with our original first 2 bits all the way at the end in a completely different spot. Now, instead of negative 58, the value would be 3. So we shifted six places. Again, let's remember that to get a true, we need a 1 or some other spot, or some other value, sorry, and then false, we need all zeros. So how do we get that from our original value? Let's take 64 and let's shift it right 6. What happens when we shift 64 right 6? We end up with 0, 1 at the end, and then a completely new number, which is nice. This number is actually the representation for true. So if we look at our integer after shifting 64, we notice that we end up with true. So it's going to say, is 64 negative? And if we return this value, it's going to say, yes, 64 is negative. But that's not true. 64 is positive. So what do we do instead? Well, we want to be able to shift this negative bit all the way to the first rightmost bit. And to do that, we can do it by, instead of shifting by 6, we want to shift by 7. We have 8 bits, so number of bits minus 1 will let us shift the correct amount. If we shift by 7, we're going to take that negative bit and we're going to put it in the front. Is 64 negative? It is not. Again, 0, 0, 0, 0 is the representation for false, so that's exactly what we wanted. Now let's take a look at a negative number. If we shifted 7 spots, or n minus 1, n being the number of bits for this number, if we shift it right 7, it's going to end up in this spot. So is negative 72 negative? After shifting, we find out that we get the representation for true, which is 0, 0, 0, 0, 1. So if we shift the number n minus 1, it will tell us whether it's negative or not by shifting the negative bit all the way to the first spot. Good enough. Let's take a different function, something else in this case. We're going to take the representation for 64. We want to create this function called last 2 bits on. We just want to figure out if the last 2 bits are on for some number. Why would you do that? Different reasons, but in this case, let's just take it at face value. So if we have the number, the integer 64, obviously this wouldn't be this wouldn't have the last 2 bits on, so we should be able to return false. It doesn't. To be able to figure out whether certain bits are on, we want to use something called a mask. And a mask is just a constant value, constant integer. A constant integer that has those 2 bits on. Why would that be helpful? Well, if we take this binary sequence that has the last 2 bits on, and we use it as a mask, and we AND it to some integer representation or sequence, then we'll notice that the original number that we had and it against the mask will result in telling us whether the last 2 bits for the original number are true or not. So in this case, are the last 2 numbers for 64 on? Using the mask, we get the value for false, which is 0. Let's take a number that does have the last 2 bits on. What would happen if we AND it against the mask? Well, in this case, we get a different number from 0, which is the value for true. And this would return whether those 2 bits are on or not.